Hey, welcome back to Calculus. In this first section of Chapter 6, it's going to be our last section of the course. We're going to take a look at the application of a definite integral, how to find the area between two curves. The diagram on the left of the screen kind of illustrates it. If you just want to look at that, I'm trying to find a method of calculating the area S when it's bounded by not a curve in the axis, but a curve in some other curve, like f of x and g of x in that picture. All right, to do that, we're going to use a definite integral. We spent a lot of time in chapter 5 learning how to compute definite integrals with the fundamental theorem of calculus, so we get to kind of flex those muscles we built up there. And then I want to show you that for some regions, it depends on the region, the area, sometimes it's better to switch the variable of integration and integrate with respect to y instead of x. Okay, so I'm going to illustrate all that stuff with examples. Let's get going. We're going to start off by kind of deriving the formula that we need to compute the area of such a region. Yeah, and so we're going to be making what is called in calculus a local estimate. If you're going to take Calc 2, you're going to look at all kinds of applications of the definite integral. This area between curves is just one of them. If you want to peek ahead in chapter 6, it's okay. You can check out, there's all kinds of interesting applications of the integral. If I'm not mistaken, it's chapter 8 is just all about applications of this integral. And in any application of the integral, you begin by making this so-called local estimate. What's a local estimate? The problem you're trying to solve, here I'm trying to find the area of that region. I just take some small piece of it. So like as usual, when we formed Riemann sums, I'd cut this interval from A to B up into a bunch of subintervals. Okay, you can see one of them right there. I'll call its width delta x. And then on that subinterval, I just pretend that f and g are both constant functions. Okay, so I just pretend their values don't change. So if they're constant functions, the area that we're trying to find is just the area of a rectangle, right? And the area of a rectangle is its height. Well, its height is the y value up here. That's the f of xi star. What's xi star? Xi star is just my sample point. So at some point in that interval, it looks like it's the midpoint, but it doesn't matter. And then I have to subtract g of xi star, right? So that difference is the height of that rectangle, and delta x is its width. And when you multiply height by width, you get area. So what am I writing over here? If you add all those things up over all the subintervals, remember what that thing is? That's a Riemann sum. And you can check it dimensionally. This is height times width, that's area. This Riemann sum is giving us area. That's the thing that we took limits of when we were computing definite integrals. If we take the limit as n goes to infinity of that Riemann sum, that's precisely the definite integral. And what's it the definite integral of? Well, f of x minus g of x, the function that bounds the region on top minus the function that bounds the region on the bottom. Okay, so let's summarize that. I'll do it with the from the text so it looks nicer. Here's the kind of answer. We just derived this formula. If you want to find the area between two curves, f of x and g of x, and it's important that in this picture, f is the curve that's on top of g. So instead of memorizing the formula from the book, I kind of like to think about it like this. You have to take the top curve minus the bottom curve. You need a graph to know which is which, but you have to subtract in the right order to get the area. Okay, and then you integrate that. You integrate that height function, f of x minus g of x, with respect to x from a to b, and that gives you the exact area. Why is this true? I'm not going to write a proof of it, but it's the limit of the Riemann sum that we were looking at above. Cool. Let's do an example. This example, I've written it out, and in fact, I've even written out the entire answer. I won't make this video long by kind of integrating polynomials with you, but I just kind of want to illustrate the formula quickly. So this is the way the problem would be phrased to you in the book. Find the area between the function f of x equals x squared and the function g of x equals minus 3/2 x, and do it over the interval from 0 to 2. So that would be the statement of in the book. You'd need to make this graph. Make a graph. Yeah, you need to visualize these problems. So this picture probably won't come with the problem like I put it here. You make it. But here we're looking at it. I've color-coded it. Y equals x squared in red. Y equals minus 3/2 x is in blue. The region we're talking about is the region between those things from x equals 0 to x equals 2, which is right here. So I've shaded it. Okay, how do we find the area of that? Well, our new formula says that we take the area of the top function. That's our x squared, yeah? That's bounding the region above. That's what I mean by top. bigger y values, whatever you like, and I need to subtract the function that's bounding it on the bottom. The thing that's bounding it on the bottom is the line, right? Smaller y values, lower in the picture, whatever you like. And that's minus 3 halves x. So if you're subtracting that, then the arithmetic says that's a plus. And again, I omitted all of the details. You should stop the video right now, find an antiderivative for this thing, evaluate it from 0 to 1, do the arithmetic, and make sure that you can recover that number 17/3. It'll make it worth your time. Okay, let's do another one. This time we're asked to find the area between the parabola x squared again and some other parabola, y equals 2x minus x squared. Okay, well, like I say, make a graph. I'll stop it. I mean, you should stop the video and go make the graph. Look at the picture yourself on these things. Okay, if you did it, you probably did it in Desmos, and Desmos probably shows you with curves crossing, there's probably points you can click on. You can find those coordinates. That's great. It's a good skill to have, and why not use it? It's a great tool. It takes a lot of, but it's also important to kind of algebraically know how to do that, especially in cases like this where the algebra is not that much trouble. So it's important skill. I'm just going to kind of do it real quick here. I need to know, what are my limits of integration? You know, unlike in the first problem, I wasn't told. I can see that this one is 0. It's the origin, but I'm not told the limits of integration. How do I find them? Well, to find two curves where they cross, it's a good skill to know. You set their outputs equal to each other. So you have to solve an equation. You have to determine the values of x that make the outputs on x squared the same as the outputs on this other parabola, 2x minus x squared. All right, so I haven't written it out, so let's just do it real quick here. That's 2x squared minus 2x is 0 is an equivalent form of that. Factor it, and you can see that x is either 0, we knew that one, or x is 1. Okay, so that's what we should put down here. We should put that x is equal to 1, and now we know our limits of integration. We have a graph, so we can see the order we should subtract. The blue parabola, the opening down parabola, is bounding the region above, right? That's the top curve. The top curve in this example is the blue one over the region. Yeah, the other one, the red curve, is the one that's bounding it on the bottom. It's the smaller y values in that region, right? Smaller y values are always down. Okay, so again, I'm going to keep the video short and just sort of tell you that the area of that region, well, you would integrate top minus bottom. We just discussed which is which. There's a little bit of the algebra. You can stop it and check that you get a third. Okay, cool. Let's do another example. Again, we're going to have to find some limits of integration. We were just given some equations, but one of these equations is kind of interesting in that it doesn't define y as a function of x. Yeah, it defines x as a function of y, but it doesn't define y as a function of x. Y is squared in this equation. Yeah, so again, we kind of need a graph. And if you go to Desmos, you should do it. You type these things exactly as you see them. You include the y equals part this time. You can just type y squared equals 2x plus 6. It'll plot it for you. And it'll show you where these curves intersect and everything. Good. But we need to be able to kind of verify all that stuff algebraically, right? That's the skill that we're trying to practice in addition to learning this calculus, is how to become proficient in these calculations and verify things. You know, maybe we're questioning Desmos or something like that. So here's what the picture, if you plotted the things on Desmos, I just clipped it here to keep the video going quicker. So y equals x minus 1 is a line. We're not surprised by that. It's a line with slope 1 and y-intercept minus 1. And this guy, well, it's a parabola, but it's opening to the right. It's a parabola opening to the right. So the blue curve, it's not a function of x, but rather two functions of x. Yeah, one of them is the positive square root of 2x plus 6, right? That function's graph looks like this. Its domain is whatever that x value is, minus 3 to infinity. The other one is y equals minus the square root of 2x plus 6. That's this part of this thing. Okay, so there's y if you want as functions of x, but you have to split that graph into two graphs so that you don't violate the vertical line test. All right, and we can see the region. It's bounded in there. It's got kind of a cool shape, and we need to know these two places. We need to know where those curves cross. So again, you need to set the outputs equal to each other. Here, I think I'm going to just try to keep the algebra a little bit light because I haven't written it out. So I have one expression for y squared. Why don't I square this thing and I'll have another one? So I'm going to start by writing, well, that quantity, x minus 1 squared, that's equal to y squared. So it should also have to equal 2x plus 6 if these things intersect. And then there we go. Yeah, so if we just kind of multiply this thing out for a second, I'm just going to gather some like terms, see what we've got here. So we would have that. Minus 5 is 0. You can stop the video and do all this without me, but it looks like we would have to factor that thing into x. Let's see, I need to get a negative 5. So yeah, let's try this. That would indeed give me the right factorization. So two values, negative 1 and positive 5 are the two x values that we should see. So we kind of know part of what we wanted. Those 2 points, well, no, that's what we wanted to know. We wanted to know where they cross. So that's at negative 1, and this one's at 5. And then we also have to have this point if we're going to set this integral up. So to find that point, we would have to set on the blue curve y equal to 0. So if 0 is 2x plus 6, then you can check that x is minus 3. All right. So that sets us up for this integral, but over this region, it is not the case that from the far left, x equals minus 3, to the far right, x equals 5, that there's one function bounding this region on top and one function on bottom. It changes. It changes at the number x equals minus 1. At that value of x, the function that is bounding this region on the bottom, the negative square root of 2x plus 6, switches to this line, x minus 1. Yeah, there are two distinct functions bounding that region on the bottom. So that means we have to do this with two integrals. We can't set it up because in our integral formula, we have to subtract top minus bottom. And if it changes, you have to stop and switch that bottom function. So this is going to need two integrals. That's the kind of summary of what I'm trying to talk about. This thing needs two integrals. Well, dx, integrating with respect to x. And let's write them down real quick. I'm going to have to scroll a little bit for the picture here, but the total area that we want, one of the integrals would be over this first interval. It would be the integral from negative 3 to negative 1. We have to pause there. And then what function's on top? It's that square root. And what function's on bottom? It's minus the square root. All right, but then we're going to have to add to that the integral from negative 1 all the way over to 5, right? That's the rest of the thing. Square root function minus the line. I'm going to run out of room here. 2x plus 6 minus that line, which is x minus 1. Okay, so I think it's doable. Let me just sort of recopy this thing real quick. I know this video is getting kind of long, but if we do a little bit of the algebra, I at least want to say something about the technique that I would use here. There, I can sort of pause right there for a second. I don't have any room, and on this one, I don't have the answers. You can come to an office hour and ask me to go over it with you, or just work it out yourself confidently. You can finish this thing. But to do this, so we have to do these two integrals. One of them, this is going to be a u substitution. Yeah, if you want a little hint, I would let u equal 2x plus 6. So that's just a square root. You're going to have to do that same substitution for this part of this integral, and the other ones you can just do term by term with the power rule. And then, a ton of arithmetic. A ton of arithmetic. I'm sorry I didn't work out an answer, and I'm not going to type it while I am doing this because the video will get too long. But come to an office hour and I'll confirm or deny what you think the answer to that integral is. All right. But I want to say something more. This is a ton of work to do this. And we could, if we wanted to switch our perspective, kind of make getting this answer a little bit easier. Okay. So let's go back to the picture here. And I've sort of got a clean slate so we can think clearly. And the trouble came about in the computation, and not the trouble, but the complexity, because we had to split this thing into two integrals. And we had to split it into two integrals because the bottom curve switched. But if we looked at this thing the other way, if we looked at x as a function of y and not the other way around, then it's the case that there's just one curve bounding things. So what do I mean by that? Let's take both of our equations and solve them for x. If I solve that first equation for x, it says x is y plus 1. That's what I mean by x as a function of y. If I solve this one for x, the blue one, if we kind of take small steps, it would say y squared, take away 6, divided by 2 is equal to x, yeah? Or if we wanted to multiply that through, we could write 1/2 y squared minus 3 is equal to x. So there's x as a function of y. And in our region, the region that we're trying to calculate, throughout that entire thing, we have one function on top. It's the line, because when you're looking at x as a function of y, on top means to the right? Because those are bigger x values. You have bigger x values to the right of this thing. So that's why that's the top function. And throughout the entire region, this x equals that 1/2 y squared minus 3, it bounds it on the bottom. So if we just take our point of view of thinking of these things as functions of y, we can write this integral down in one integral. We need to know the y coordinates of those 2 points. We have to know, remember we knew that this was x equals 5, and that's x equals minus 1, but you have to know the y coordinates as well. Well, they're on the line. This is where I would do it. They're on the line y is equal to x minus 1. So the y coordinates there, this would just be the point 5, 4, and this would be the point minus 1, minus 2. Yeah, because they have to subtract 1 from the x coordinate to get the y coordinate. So the area in a single integral is the integral from what's the smallest y value, minus 2, to the biggest one, 4. What function's on top? Remember, to the right with respect to x, that's our y plus 1. Subtract the thing that's on the bottom. That's our 1/2 y squared minus 3. And we're integrating that, quote unquote, dy. That's our variable of integration this time. We've looked at the problem kind of vertically, if you like. So if you do a little bit of algebra and clean that up a little bit, you'd get what? Minus 1/2 y squared. We have the plus y, and then we have plus 1, plus 3, so it looks like plus 4. Okay, and you can check, so I guess I do have an answer after all, ha ha ha, to the problem above, that this integral computes out to be the number 18. Okay, but if this integral is 18, then so is the other one, and the other one would be much harder to compute. I'm kind of hoping you stopped and computed that because it's good substitution practice, but there you go. So what's the moral of the story? By switching the order of integration, quote unquote, we made the arithmetic a little easier. Well, will it always happen? No, it depends on the region, but in this particular region, it was easier to describe it by looking at x going between two functions of y, because then we didn't have to use two integrals. Cool. Okay. Last topic in this long video is sometimes you want to know the area between curves and you don't mean it in the sense of signed area. We've already thought about this in the context of like calculating distance instead of displacement, for example, right? When you calculate distance, you want to know the integral of the speed, not just the velocity. So all of these areas, S1, S2, and S3, if you're looking at the picture, we want to know the sum of them. We don't want to count S2 as a negative, okay? So that requires more than one integral, because our formula, you have to integrate top minus bottom. And if the top and bottom switch, like they do at around that point right there, then you have to split the integral there. Okay, so let's set up one example to illustrate that. I've got a little hand-drawn picture here. I hope it's not too crude, but let's compute the area of the region between cosine and sine from 0 to pi. So I've got them drawn there. You can look at their labels and colors. And I want this total area. If we use the notation above, I want to find S1 and S2. Yeah, but the curves cross. Where do they cross? Well, they cross where cosine is equal to sine. That has infinitely many solutions, but between 0 and 2 pi, there's only one, and it's pi over 4, yeah, from the unit circle. Cosine and sine are the same, or tangent is equal to 1 if you prefer, at pi over 4. So we have to split this integral at pi over 4. So to set this thing up, we're going to have to integrate in one order. I think I've got this ready to kind of reveal to you. We're going to have to integrate from 0 to pi over 4 cosine minus sine. Why? Because from 0 to pi over 4, the cosine curve is on top and the sine curve is on bottom. So I have to integrate in that order, cosine minus sine. But from pi over 4 to pi, we can go back and look at the picture if you want, but they switched. They switched. So I have to integrate sine minus cosine. Okay, I'm going to leave the details to you. It's excellent practice, unit circle practice, antiderivative trig practice, just good for your brain in general. But I'll tell you, after you've done that practice, I hope you stopped it and looked. But yeah, the first integral should give you that, minus 1 plus root 2. The second one should give you 1 plus root 2. And those things to sum together to give 2 root 2. So that's the answer you should get. And I hope that you'll do it. Okay, well, that's it. This video is a little long, but it was fun. Thanks for listening.